All right, so these are the notes on waves. You've already looked at a waves gizmo, so some of this information should be familiar. And you had the couple of videos that you looked at that were an introduction to waves. All right, so this right here, I went ahead and crossed out just because this is an older version of the book that you have, so these pages are no longer correct. So you might want to just cross it out or something or ignore it. But again, those are not, they don't go with your textbook. They go with an older version of the textbook that you're currently using. So those pages are going to be slightly off. All right, so talking about waves. A medium is the material or matter through which something such as energy passes. So when you hear us talk about medium, we're talking about matter. All right? So examples would be earth, water, air. Anything that is composed of matter, anything that is composed of particles is going to be a medium. All right? So the table, it could be a pipe, it could be your anything. All right? Anything that is composed of particles is considered a medium. So the reason that we're talking about this is because we're talking about a specific type of wave today which requires a medium to travel, all right? It has to have particles to travel on or it doesn't exist. So a medium is the material, the matter through which something such as energy passes. And that is what we're looking at. Waves are energy. Okay, make sure on your screen, your Zoom screen, you hit the little button top right. Looks like arrows out to make it full screen. This is about as big as I can blow it out without losing information.
You can make it a little bit bigger for like people on the Chromebooks. You can open up a window with OBS, and it'll give you a windowed preview. You can right click on the gray area on the side of the screen.
All right, so the next reason that we're talking about medium, because there are certain waves that require a medium in order to travel. So that would be a mechanical wave. So mechanical waves are waves that require a material medium for transmission. Okay, so example would be sound waves. Ocean waves, okay, they use water particles. Now, as far as sound can travel through any matter. So it can travel on air, can travel through solids, can travel through liquids. But when we say that it requires a medium in order to travel, that means if there are no particles are available, or if particles are so spread out that the wave is not able to travel in the particles, then that means that wave is not going to exist. All right. So if you are in a vacuum or you're in empty space, as it says here, sound waves need medium to travel on. So just like when you're talking, right? What you're doing is you're causing vibrations in the air, right? So sound actually travels on air. If you are in empty space, then there are no particles. So you can try to scream, but nobody's going to hear you, all right? There will be no sound because it requires the particles to travel on. Okay, so that was for mechanical waves. So mechanical waves are the ones that require a medium. Later on, we're going to just talk briefly about electromagnetic waves, which are ones that can travel, waves that can travel in the absence of particles. They can travel through empty space, all right? But the focus of these notes, these are for mechanical waves, ones that require medium to travel on. Okay, pulse wave, a wave that consists of a single traveling pulse. A wave that consists of a single traveling pulse. So what would happen is if, let's say I had a slinky, and all I did was I took the slinky, I was holding the slinky, and I just flicked it out to the side one time. All right, so you have one wave that travels down. That is called a pulse. All right, so one movement only, not continuous. Just like one flick of the wrist, wave travels out. All right, that would be a pulse, a wave that consists of a single traveling pulse. And then you have the other kind, which is called a periodic wave. So what happens is if your source continues to repeat, so I'm holding the slinky, and what happens is I keep my motion going, all right? So the wave is continuous. Then what that is a periodic wave. A periodic wave is a wave whose source is some source of periodic motion. It's a repetitive motion, all right? That would be a periodic wave. All right, so two types of mechanical waves that we're going to be talking about are transverse waves and longitudinal waves. So transverse wave, and this is where for number 2 and number 3, you're going to have to draw pictures. So make sure you leave some room. So it says define and diagram a transverse wave, label all parts. So wave motion is perpendicular to particle motion. This is for a transverse wave. Make sure you leave room to draw a diagram. Your wave motion is perpendicular to particle motion. So example, it says moving sideways, up, down, motion of a slinky. Go ahead and write that down, and then I will show you an example. Wave motion is perpendicular to particle motion. So you want to think about the way that the energy is moving versus the way that the particles are vibrating. Because remember that we're talking about waves that require a medium or they require particles to travel on. So which way are the particles moving? Which way is the energy moving? If they are moving perpendicular to each other, 90-degree angle to each other, then it is a transverse wave. All right, so right here is your example of a transverse wave. So this hand, what this hand is going to do is move in up and down motion and look at the wave that's going to be generated. And what I want you to do is pay attention to the coil. So which way are the coils moving, all right? Not all together, maybe just focus on this coil or focus on this coil. Just look at one of them and look at the direction of the motion. And then also look at the way that the wave energy is traveling. All right, so if you're looking at one of these coils, which way is it moving? So you can say up, down, left, or right. Which way is it moving? It's moving up and down, all right? Now the energy in the wave itself, which way is it moving? Which way is the wave energy moving? Do you see a wave? It's moving to the right? All right, so this way. So again, your particles or your medium, the direction that these are vibrating in is perpendicular to the motion or the direction that the wave is traveling in, that energy. So when we're talking about waves transfers energy only. It does not transfer matter, okay? So for example, we said sound travels on air, right? Sound is generated in me. Have you seen the like movies or examples where somebody can sing a high frequency, a certain note, and break glass? Yes? Okay. Now, if I had a rock in my hand, can I just toss that rock up in the air and then it's going to break that glass that's way back in the back of the room? If I want to break the window with a rock, what do I have to do? Have to throw the rock at the window, right? So in that case, what happens is, yes, the rock has energy, but in order to get that energy to the window, for it to do work on the window, then what has to happen is the matter, the rock has to actually go with the energy, all right? So when you throw a rock, you have matter being transferred with the energy. Both of them are moving. In this case, you see that the particles are moving up and down, but the wave, the energy is still able to move forward, all right? So energy is being transferred only, not the waves. Waves are vibrating, the energy is traveling on the waves, but the matter still stays pretty much where it is, just vibrates in place, up and down, or sideways if it's going to be a sideways motion. In this case, it's up and down, all right, and it's just the energy that moves. So waves transfer energy only. Waves transfer energy only. Okay, so what you need to draw in that space for transverse waves is this, all right? So you want a center point, a center line. It's like your line of equilibrium, all right? And then you're going to draw this wave, okay? And then there's certain things that you need to label. Now, as far as this, your height from the equilibrium here and your lowest point here, this is called, the top of this is called the crest. The lowest point is called the trough. From equilibrium to the trough, equilibrium to the crest, they should be equal as far as an equal height. Okay, and what that is called as far as that displacement from the center, from that equilibrium point, it's called your amplitude. Amplitude is measured in meters. Yes, you need to draw this in your space for transverse waves and make sure to label it. All right, so amplitude is your displacement from the equilibrium point. Can be measured here from center to the crest, or it can be measured from the center to the trough. That's your amplitude. And again, those two should be the same. It's measured in meters. Your crest is the highest, the peak of your wave, and trough is your lowest point on the wave. And then the last thing that you need to label is what's called a wavelength. Okay, wavelength is the length of one complete wave. All right? So usually it's measured from crest to crest or from trough to trough. But basically what you're looking for is the distance to the next point, the next similar point. So if I could measure it from here too, all right? If I was reading this as if I was reading, reading from left to right. So when I get to this point and I'm tracing this wave, if I get to this point, I'm at equilibrium and I'm traveling up. So I need to find the next point where I'm at equilibrium, but I'm about to travel up, all right? So from here to this, would this be the end of the wave? No, because I am at equilibrium, but I am traveling downward. In this case, I was traveling upward. So that would be right here. So from here to here would be a wavelength, all right? Doesn't matter what you use, the wavelength is going to be the same no matter which one you use. So I could measure from here to here. I can do crest to crest. I can do trough to trough. You're just looking for the next similar point. I can measure from here. Okay, so this is at equilibrium headed downward. Well, the next equilibrium headed downward is here. So that would be a wavelength too. All right? But wavelengths, wherever you choose to measure, it's going to be the same. all right? And again, it is measured in meters. So the length of one wave is a wavelength. Your amplitude is your displacement from the equilibrium of the center point, okay? That's how high the wave is. Now, in terms of sound, amplitude is related to your loudness, all right? So the larger the amplitude when it comes to sound waves, the larger the amplitude, the louder the sound is going to be. Anyone still need this? Okay, so the next part is longitudinal wave. So again, you're going to write your information in there, but leave room to draw. So this is a wave in which your wave motion is parallel to particle motion. Wave in which wave motion is parallel to particle motion. So your wave motion, your energy from the wave, is moving parallel to the direction the particles are moving. Whereas here, they were perpendicular. The example that you saw, the particles are moving up and down, while the wave was moving to the right, perpendicular. So in this case, they are moving parallel to each other. Okay, so this would be a longitudinal wave. In this case, the hand, rather than lifting this up and making it move up and down, all it's going to do is pull back on the coils. So watch which way or push forward. So look at the way that the coils are moving. All right? So your coils, the wave itself is still traveling to the right, but your coils, as far as them vibrating, they are back and forth this way. So again, that is parallel to the direction of your energy. So in that case, that is what would make a longitudinal wave. So you're drawing for this. You can make it however you want to. You can have coils where you have them tight together, because if you notice, there were areas in the video where they were tight together, they're close together when they got compressed, and then there were areas where the coils were more spread out. So you can do something like this. You can do something like this. You can make it prettier. Use your own unique talents. I am not an artiste. All right, and then the things that you need to label, the areas where the coils are close together, the area of compression, and the areas where they are more spread apart, is the area of rarefaction. So again, with your longitudinal waves, your coils or your particles vibrate in a direction parallel to the direction the wave is moving, the energy is moving. Okay, here's a question, and just put yes or no in the chat, please. Are both matter and energy transferred in waves? Just in the chat, put a yes or no. Are both matter and energy transferred in waves? Good. Okay, the answer is no. So which one of those is being transferred in waves? It's the energy. Good. Okay, so again, when we say matter is not being transferred, If you think about a slinky, if I am, once I get the wave moving in a slinky, I'm still holding on to my end of the slinky. I don't need to let it go for that energy to get to the end of the slinky, to the other person that's holding the other end. The wave, the energy is still going to go, but the particles are still, they're vibrating back and forth or up and down, but they're still in that area. They don't have to move with the slinky, all right? So it's the energy that is getting transferred, not the matter, all right? Not like when you're throwing a rock, all right, where both matter and the energy in the rock are being transferred together. Does anyone still need this picture? All right, the next thing on the notes. Regarding the compression and the rarefaction. So a compression corresponds to crests in a transverse wave. Compression in a longitudinal waves, those areas that are squeezed together, correspond to the crest, the highest point on a transverse wave. That is the area of high density and high pressure. So you think about in a longitudinal wave, when you're looking at it, those particles are close together. That's compressed, all right? So you have more particles in a given area. That's going to cause higher density, and it's also going to cause higher pressure in that area. A rarefaction, on the other hand, rarefaction in a longitudinal wave, that area where they're spread out, particles are more spread out, so that means it's going to be less dense. You have fewer particles within a given area, which means that's also going to be an area of low pressure. All right, so corresponds to the trough, the low point on a transverse wave. Okay, next thing that we're going to talk about is period and frequency. I'm going to go ahead and give this to you, and then I will show you the diagram. So period is the amount of time required for one complete vibration of the particles, one complete cycle, okay? For one wave to form, if you're looking at moving around in a circle, like if we're looking at, we did use the word period when we were looking at circular motion. So when something is moving in a circle, like we had the stopper on the string, one complete circle would be the time it takes to complete one circle would be a period. So the time it takes to make one complete wave, okay, is going to be a period. The amount of time required for one complete vibration of the particle of the medium. Complete one circle, time to take to complete one circle, time it takes to make one wave, complete one wavelength. All right, so it is a time. It's measured in seconds. And your frequency is the number of waves per second. So whereas with your period, you're looking at the amount of time to make one wave, your frequency is, if I had to measure time, like 1 second, how many waves are actually produced in that second? All right, so that's going to be your frequency. So frequency is measured in cycle or in hertz. Okay, so the way we look at frequency, hertz is, if you were to break this up, it's like 1 over second. We say cycles over seconds or waves per second, but that's waves, cycles is kind of an imaginary unit. We don't write that in there, so it's 1 over seconds, or it would be s to the negative 1. Okay, and the relationship between period and frequency is that they are the inverse of each other. So if you know one, if I know the frequency, if I do 1 over frequency, it will give me a period. If I know the period, and I do 1 divided by the period, 1 over t, then I will get the frequency. They are the inverse of each other. Okay, so period is measured in seconds, and there's another line that's on the next page for this section. What is frequency measured in? Period is measured in seconds, and frequency is measured in what? Go ahead and put it in the chat, please. Period is measured in seconds, and frequency is measured in hertz. Good. Does anyone need this last part? I can switch to the next page so you can get, like I said, there's one last line for this number 8. And let me know when you're finished. Okay, if you still need it, go ahead and screenshot it because I'm changing the page. All right, so this was the last line. Still for number 8 was frequencies measured in hertz, or s to the negative 1, or again, 1 over s. You can also write that as 1 over s. Right, number 9. Write an equation that relates period, frequency, and wave speed. State the units for each variable. So period, frequency, and wave speed, this is similar to a velocity equals distance, displacement divided by time, v equals d over t equation. All right? So in this case, we have velocity equals frequency times wavelength. Okay, lambda stands for wavelength, which is in meters. And the F stands for the frequency. So if I was to plug in units, I didn't plug in hertz. What I did was I plugged in the 1 over s for frequency, and then for wavelength, I typed in m for meters. So when you multiply this out, you're going to end up with meters per second, which are the units of measurement for your velocity. So you can look at it as a frequency times wavelength, all right, or lambda f, v equals lambda f. Or you can look at it as v equals lambda over t, okay? Wavelength divided by period. Wavelength, again, is measured in meters divided by your period, okay, which is seconds. All right, so I'm going to switch to another screen where you can look at a diagram for just your frequency as it relates to period, and as it relates to wavelength. All right, let's take a look at this diagram for a moment. All right, so let's draw a line. I'm going to draw a vertical line here and a vertical line here, just imaginary lines. And we're going to say that this is for the wave that is produced during a 1 second period of time, 1 second. All right? Now remember that as far as your wave, you can just whatever point that is similar to this. So this one's headed down. It looks like it'll be about right here where this wave will end. So that's one wavelength. And we're looking at two wavelengths that are here within this 1 second. All right? So we have two wavelengths here. Your frequency is how many wavelengths you are able to produce within 1 second. And I just said that we're going to use this as 1 second. So what I have here, 2 waves per second would make this 2 hertz. All right? Well, what would this be if we did that same method? So for this, I went from here to here is 1 wave. And from there to there is 2 waves. So this is 2 hertz per second. What would be the frequency for this yellow one? What would be the frequency for this yellow one? How many waves do you see produced here? And if we're saying that this is 1 second. 3. Okay, so let's see. It's got 1, 2. Not quite 3, but almost. So it would be 3 if it was coming up. So it might be what, 2, and what would you say? 2 and maybe a little bit more than a half, 3/4, 2.5. Okay, so this is 2, this is 2.5. Now, what happens is you see your frequency is increasing, which means we're getting more waves per second. What's happening to your wavelength? What's happening to the length of your waves as your frequency increases? Yeah, we can say 2.5, 2 3/4. So what is happening to as our frequency is increasing, this is increasing, what's happening to your wavelength? The length of one wave. Is the wavelength getting longer or the wavelength getting shorter? So just real quick look at from crest to crest. Look at the length from here to here, this length versus this length versus this length. Okay, so as we're moving down, our frequencies are getting higher, we're producing more waves. So yes, your wavelength is going to decrease as you're producing more waves. But that also means, remember that as far as your period is the time to produce one wave. So as our frequency increases, what happens to the period, the time that it takes to produce that one wave? How much time does it take to produce this wave? Remember that this from here to here is 1 second. So producing a wave, this wave, versus producing this wave. So as you increase your frequency, what is happening to the period, which is the time it takes to create one wave? Put your answer in the chat. So we see that frequency is increasing as we move down. What is happening to the period as we move down? Does the time it take to make this wave get longer or shorter? Is the time it takes to make this wave longer or shorter than the time it takes to make this wave? It gets shorter. So frequency increases as frequency goes up. Your period, the time to make one wave, goes down. All right, so that's where we're saying that they are inversely related. All right, they are the inverse of each other. Okay, so to finish up for today, I'm going to switch back to the notes. And what I want you to do is get down the definition. You're supposed to draw a diagram in here. You may have room to fit it in there. So just go ahead and write down the definitions for constructive interference and destructive interference. So constructive interference and destructive interference has to do with what happens when you have waves that are headed towards each other. So constructive interference says interference in which displacement's on the same side of equilibrium, meaning if I had a slinky, all right, long slinky, I have someone start a wave on this side, I have someone start a wave on this side, and they're both headed up. So what happens is when they meet, the question is what's going to happen. If they're started on the same side, then it should be constructive interference. Constructive means it's going to build. So the wave, the resulting wave that you get when they reach each other should be bigger than what they were apart. Destructive interference is where you have one wave on one end of a slinky. Slinky is just an example of the matter we're using. Starts up, and the other person starts it down. Okay, so what happens is when they reach each other, they should cancel each other out. Destructive interference. So constructive interference is where you're building them, making them bigger. And destructive is when you have your two waves meet, they actually break down or end up with a smaller wave or canceling out waves. Okay, so we only have a minute left in class. I'm actually going to stop it right there, and I will give you the diagrams. Next time we'll talk about those. All right, so are there any questions right now?